This conference will now be recorded.
Hello everyone. So silica, we have already seen its that is preparation methods, the reactions by which we can make it. Now we will see its properties. Once we have finished silica, next we will start silicon carbide and silicon, the important compounds of the element silicon. So silica, the properties, the compound is actually very inert in nature. It will not take part in reaction under normal condition. And with most of the common substrate, when I'm saying common substrate, it means hydrogen, oxygen, halogen. So these are the common substrate with which we compare any chemical properties for any compound. Okay. Now for silica, because of its inert nature and also the high melting point. Now why the melting point is high? Because this bond, SiO bond, is very strong. Now to break this bond, very high amount of energy is required. So that is the reason it has very high melting point. And because of this high bond energy of SiO bond, there is no reaction with halogens, though there is exception, only fluorine reacts, and fluorine is the most reactive halogen, so that is why it reacts only with fluorine. But with other halogens like chlorine, bromine, iodine, there is no reaction. Then with dihydrogen, that is molecule H2, there is no reaction. Then most of the common acid. By common acid, I am trying to say HCl, H2SO4. So there is no such reactions with these acids. And also there is no reaction with metals, even if you are doing that reactions at high temperature. Okay. Now there is only some specific reactions, 2 to 3 specific reactions for this compound silica that we will see here. The first reaction here, as you can see, number 1, reaction with HF. So this is the only acid with which there is reaction of SiO. But with HCl, HNO3, H2SO4, there is no reaction. So silicon dioxide reacts with HF, which is basically hydrofluoric acid. And the compound is, that is the product that we get, is SiF4. But this is the compound. It depends on what is the mole ratio. So suppose the mole ratio is 1:4, then first we will be getting SiF4. But if there is excess of hydrofluoric acid, now there is formation of H2SiF6, which is hexafluorosilicic acid. So depending on whether it is 1:4 mole ratio reaction between SiO2 and HF, or it is 1:6 mole ratio, depending on that we can get different types of product. So it is either SiF4 or H2SiF6. Now because of this particular reaction, HF acid cannot be stored in glass bottles, because in glass bottles there is presence of SiO2. And how this acid is stored? HF is stored in containers that are made up of metal alloy or copper. Fine. The next reaction of silica is reaction with only one halogen with which it reacts, and that is fluorine. So with fluorine, silicon dioxide reacts and it produces again SiF4, and oxygen is the byproduct. So here SiO bonds are broken and we get SiF bonds. The third reaction is with NaOH, but look at the temperature. We can have this reaction only at very high temperature, 900 to 1000 degrees centigrade. So silicon dioxide reacts with sodium hydroxide to produce sodium silicate and water at a temperature 900 to 1000 degrees centigrade. So SiO2 reacts with 2NaOH. The reaction is 1:2 mole ratio, and we get Na2SiO3, which is sodium silicate. And there is also the byproduct, which is water. So these are the three reactions. So remember, silicon dioxide or silica, it reacts with HF, it reacts with only one halogen, which is F2, and it reacts with sodium hydroxide at very high temperature. So these are the three compounds with which basically two compounds, HF and NaOH, F2 is element. So these are the three substances with which it reacts. Okay. Application part of silica In petroleum industry as a catalyst, it is used. Then in the production of glass and elemental silicon. That means starting from silica, we can get elemental silicon as an anti-caking agent in powdered foods like spices. So sometimes in food, some anti-caking agents are added so that the food, if we want the food to be in powder form only, so in that case, some anti-caking agents are added, and silica is one such anti-caking agent because it has some moisture absorbing property which helps to maintain the food in powdered condition. Fine. In pharmaceuticals for making tablets, then in toothpaste to remove tooth plaque, building sector to make concrete, and as a drying agent, as I have said, there is some moisture absorbing property. As a drying agent, as an absorbent for chromatographic materials. So in chromatography, especially with organic compounds, if we have impure organic compounds or mixture of 2 to 3 organic compounds, then we do chromatography for separation to get pure organic compound. So in that case, in the glass column, as absorbent for the organic compound, that is which we are trying to make pure, there in the column silica is filled, that is the column is filled with silica and it acts as absorbent for the compound which is to be purified. Some more applications. So we know that quartz is a form of silica. It is used as a piezoelectric material. Now piezoelectric material are those materials that can generate electricity when there is some mechanical stress or strain. Then Kaisergard, it is the amorphous form of silica. Quartz is crystalline form, but Kaisergard is amorphous form of silica which is used in the filtration plant. Then there is a complex NH4-2COCl4. If you remove these two ammonium, the complex is like this: CO with 4 chloride, and there is 2 negative charge. These 2 negative charges are actually balanced by 2 ammonium plus ion. Now what happens? This complex is added to silica gel, and this combination can be used as humidity detector, because when this complex is in dry condition, now it is having color blue, but in presence of water, because silica gel, it has some moisture absorbing property. So suppose this mixture is kept somewhere where there is humidity, so this moisture will be absorbed by silica, and as there is presence of this complex, so in presence of that moisture, this complex now it will be converted to aqua complex like this. So in presence of this complex, now the color is different. It is pink. This is a hydrated state where all the chloride ligands are replaced by water molecule. So because of this change in complex structure, because it is already added to silica gel, there is a drastic color change, blue to pink. So in this way, we can understand whether there is humidity present or not. So this is humidity detector. In its crystalline form, because there are two forms, either crystalline or amorphous. So in crystalline form, it can be used in hydraulic fracturing. Now this method is basically commonly known as fracking. It is a process of injecting water, sand, or some other chemicals, just like this. This chemical can also be used into a well to break up underground bedrock so that we can free up oil or gas reserves. So this is the purpose of this process, which is hydraulic fracturing. And in hydraulic fracturing, water, sand, and other chemicals are used. Silica is one such chemical. So these are the application parts of silica. Now we will solve question related to this compound. The ground glass stopper is often seen to get stuck in the neck of glass bottles. So there is glass bottle and there is a stopcock like this. Okay. Now if it is stuck and there is inside there is NaOH solution. Now this glass is, there is presence of SiO2, right? And we have seen that SiO2 reacts, 3 specific compounds are there. One is HF, then there is F2, and then there is NaOH. So this is one such compound with which SiO2 can react, and there is formation of Na2SiO3, sodium silicate. So this is the actual reason why the glass stopper, it is often seen to get stuck in the neck of the glass bottles. And we have to find the reason. So if you look at the options, it is the first one is saying that formation of solid sodium carbonate around the neck, because atmospheric carbon dioxide is reacting with NaOH that is kept in the bottle. But that is not the actual reason. The actual reason is formation of Na2SiO3, because in the glass there is presence of silica, and this silica is reacting with this NaOH, and that is why there is formation of sodium silicate around the neck of the bottle. Creation of partial vacuum due to highly hygroscopic nature of NaOH. This is also not the correct reason. High coefficient of thermal expansion of glass, that is also not the correct reason. So option B, that is the correct option. Next question, the amorphous form of silica is. So this is simply memory based question, and in the last class it is mentioned that different forms of silica. So quartz, cristobalite, tridymite, these three are actually crystalline form, but this one is not crystalline, it is amorphous. So this should be the correct answer. SiO2 is attacked by which one or ones? That means it may be more than one correct answer. Here we have total 4 reagents: HF, hydrofluoric acid, concentrated HCl, hot NaOH, and fluorine. Now we have seen that reaction of silica is very specific because the molecule itself is very inert in nature, and it can react only with some specific compounds. So it can react with HF, and there is formation of SiF4 and hydrogen gas. Basically, if we balance it, it will be 4HF. Then SiO2, it also reacts with fluorine, and there is formation of SiF4 along with oxygen gas. It also reacts with NaOH only at very high temperature, 900,000 degrees centigrade. This type of range of temperature, if we can maintain, there is formation of sodium silicate and water. Okay, so these three, except concentrated HCl, the other three, 1, 3, 4, there is reaction with SiO2. That means SiO2 can be attacked by these reagents. So these three are the correct options. Okay, 3 reactions. In silicon dioxide, there are double bonds between silicon and oxygen. So all these 4 statements that you are seeing in the options, that is basically related to silicon dioxide. And the first option is saying that there are double bonds between silicon and oxygen atoms. So it should be like this. But actually we know the structure of silica is not like this. If you draw the structure of carbon dioxide, both carbon and silicon, they are from group 14, right? But only for carbon, the oxide structure is like this. There is double bond between carbon and oxygen, and it is gaseous in nature, but SiO2 is not like this. So this structure is not correct. Fine. Then each silicon atom is surrounded by 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. And the next one is saying silicon is bonded to 2 silicon. But see, there is no such silicon-silicon bond. So this is not correct. Fourth one is saying that each silicon atom is surrounded by 2 oxygen atoms, and each oxygen atom bonded to 2. That is, both silicon and oxygen, they are surrounded by the other element, and in both cases it is 2 atoms. But actually that is not the case. If we see the partial, if I draw the structure, then both sides of oxygen there is 2 silicon. But for silicon, see, so this is the 8-member ring, but there are more bonds surrounding silicon. Total 4 bonds surrounding silicon, and there will be 2 more oxygens I have to draw here, and the structure will continue. So basically what we are seeing here, if we observe carefully, you will see surrounding silicon there is total 4 oxygen. But if you focus on a particular oxygen, there is actually 2 silicon. So each silicon is surrounded by 4 oxygen, and each oxygen is bonded to 2 silicon. That is actually correct option. So option B is the correct option. Okay. Next question, that is also related to silica. It is saying that silica reacts with a hydride of superhalogen to form X. Now remember, what is superhalogen? Halogen we know F2Cl2 Br2, all these molecules, that is elements of group 17. But when I am saying superhalogen, it is basically fluorine. Why it is called superhalogen? Because this is the most reactive halogen, the first member of group 17, and this is the most reactive, so it is also called superhalogen. So silica reacts with hydride of superhalogen. What is hydride of superhalogen? It is nothing but HF. Okay, and we have already seen that SiO2, it can react with HF. Even if you don't balance it, is it okay? You just have to know what is the compound that is formed. SiF4 is the compound, and there is also formation of water. But actually what is formed here? Here SiF4 is formed. Okay. Next is, so this is superhalogen to form X. So this is X. Now on hydrolysis of X, another compound Y is formed. Now when I am hydrolyzing X, there is formation of Y. That means X is reacting with water. And Y on heating at 1000 degree. Now I am heating Y at 1000 degree centigrade. It is losing water, minus water, and there is formation of Z. So these are the informations that is given. And it is at the last sentence, it is asking that Z can also be prepared by the reaction. So Z can also be prepared by which reaction? That is actually given in the options. So first of all, we have to write how X is reacting with water. We know X is SiF4. Now when SiF4 is, we are having hydrolysis of this molecule, there is formation of all the F replaced by OH, silicic acid. If you balance the reaction, there is also formation of H2SiF6, but this much information is enough to solve this. SiF4 hydrolysis, all the fluoride, that part will be replaced by hydroxide. Okay, so this is actually Y. Now, if Y is, we are heating at 1000 degrees centigrade, there is loss of water. Now, when there is loss of water, what will happen? There is actually formation of SiO2. So here SiO2 will be formed and two water molecules that are removed. So this SiO2 is actually Z. Now SiO2 can be formed by which reaction? If you look at the options, the first option, basically we have to prepare SiO2. We have to prepare Z, because in the last sentence it is mentioned Z can also be prepared by which reaction? That means you have to prepare Z. So SiO2 must be on the right hand side of the equation. The first equation that is given, it is SiO2 reacting with HF, as if we are producing SiF2, but that is not, we are making. Z is SiO2, so SiO2 cannot be in the left hand side, right? So this is not correct. Now the second one, it is preparation of SiO2. When silicon direct reaction with O2, there is formation of SiO2. Now this is only the correct option. And the third one, as if here we are making either Ka for Si, but that also we are not doing, because Z is not Ka for Si. In the fourth reaction, here in the product side we have hydrogen gas and sodium silicate, but here we are not producing sodium silicate. So correct option is option B. Okay, so here X is SiF4, Y is when we are hydrolyzing X, and Z is SiO2. So whenever you are getting this type of that is informations given, and you have to find X, Y, Z that are unknown, just write X, Y, Z in this format, write all the reactions so that you can see all the informations given in the question in front of you. and then you can decide that which is X, Y, or Z. Right? So after finishing silica, our next important compound of silicon is silicon carbide. Silicon carbide, mostly known as carborundum. You should know this name also. That is the common name which is used for silicon carbide, because suppose you are getting some question where instead of mentioning the name of silicon carbide, suppose it is mentioned as carborundum, but it actually means silicon carbide. Okay, so that is why we should also know the other terms that are used for silicon carbide. Now this carborundum occurs in nature, that is the natural form in nature is rare mineral which is known as moissanite. So moissanite is silicon carbide mineral, which is the main component of this mineral. Appearance is rock-like appearance made up of crystals, usually shiny black, although it can take on yellow or green colors. How we can prepare it? It is true that naturally we can get it in this mineral which is moissanite, but remember this naturally occurring silicon carbide mineral, moissanite, is extremely rare. It is not found, it is not very common, rare mineral. So that is why we can prepare it industrially by some method which is known as Acheson method. Now in this method, silica sand is treated with finely ground coke. So look at this reaction. SiO2 plus 3C. SiO2 is nothing but silica sand, because the main component of silica sand, 98 to 99%, is nothing but SiO2. When it is treated with finely ground coke carbon, amorphous form, you know there are different allotropes of carbon that we have already seen in this chapter. That is when we have discussed the topic allotropes of carbon. So this is one of the form, that is coke carbon, amorphous. So when these two are mixed together and heated at very high temperature, so you have to maintain this temperature. And as this temperature is very high, we have to do this reaction in electric furnace. So when we maintain this temperature, there is formation of SiC and CO. But remember, there is actually stepwise reaction. But here the reaction that you are seeing, that is actually the net reaction. If you ultimately write the equation, combining all the steps, then you get this net reaction. And this is highly endothermic process. Why highly endothermic? Because you know SiO2 inert in nature, it doesn't take part in reaction very easily. So if you want SiO2 to react, obviously you have to provide very high temperature, and this process requires a lot of temperature, so that is it is endothermic process. And we are doing this reaction at 1600 to 2500 degrees centigrade. But we have to be cautious, because if the temperature is greater than 2500, there is a problem of decomposition of our desired product SiC, which we do not want. So temperature must be in this range so that there is no further decomposition of SiC. So when SiC is decomposed, it is actually decomposed to the elemental state, that is carbon, which is graphite, and silicon. So if you heat SiC at greater than 2500 degrees centigrade, we get the elements silicon and carbon. Fine. But that is at very high temperature that we have to avoid. So this temperature we should maintain during the preparation of SiC, silicon carbide, and the method is known as Acheson method. Structure of silicon carbide. So as you can see in the right hand side, there is a large network type of structure. Now just focus on carbon. Surrounding carbon, there is total 4 carbon Si bond. And if you focus on silicon, surrounding silicon also there is 4 SiC bond. And in both cases there is tetrahedral environment. That is, if you consider Si as central atom, then the environment surrounding it is tetrahedral. If you focus on carbon as the central atom, then also surrounding it there is tetrahedral environment. So silicon carbide crystallizes in a close packed structure covalently bonded to each other. That is silicon carbon covalently bonded to each other. The atoms are arranged so that 2 primary coordination tetrahedra, where 4 carbon, 4 silicon atoms are bonded to central silicon carbon atoms, respectively. So in this way, tetrahedral arrangements are there. And if we take a particular tetrahedra, so here what we have done, central atom is carbon. That is the yellow circle, that is carbon. And this bond is carbon silicon bond. So this carbon silicon bond, which is B, it is 1.89 angstrom. But if you consider SI-SI distance, don't think it is SI-SI bond because there is no SI-SI bond. So I am saying just SI-SI distance. So the A that you are seeing here, it is distance, it is not bond. This distance is obviously high compared to carbon silicon bond distance, and this is 3.08 angstrom. These tetrahedral units are linked together through their corners and stacked. So suppose this is one tetrahedral arrangement, then this is one of the corner, then through this corner there is another tetrahedral arrangement. So it will continue all these 4 sides of these 4 corners of one particular tetrahedral. SiC acquires a high hardness, and that is expected from this type of large network covalent structure, right? Because if you want to melt it or boil it, obviously you have to break all these covalent bonds, multiple covalent bonds you have to break. So that is why it is very hard in nature. We cannot melt or boil it easily. So this is why the molecule is very rigid, capable of forming crystalline groups. And see, this compound has a special character. It is the best example of polytypic type of material. What is polytypic material? These are those materials that can vary their crystalline structure without altering chemical composition. Okay, so best example of polytypic crystalline substances. After structure, we will see properties. Now, it is having some chemical properties you will not see much because you can understand from this structure. As this is a large network type of covalent bond structure, so it is very rigid, hard, it cannot take part in reactions easily. But some other interesting properties are there for silicon carbide, and that is interesting electrical properties because there is some semiconductor characteristics. So when we consider conductivity, details you will get in the solid state chapter of class 12. So when conductivity is very good, we call it conductor. When it is very bad, it is insulator. And when we have conductivity in between, that is not very good like conductor or not very bad like insulator, but something in between, then it is considered as semiconductor. So this compound is also having some semiconductor characteristics. It is resistant to most organic and inorganic acids. Fine. Alkalis, salts in a variety of concentrations except to hydrofluoric acid. That means though it is not reacting with all these common organic acid, inorganic acid, alkali, salts, but there can be reaction with HF, which is hydrofluoric acid, and acid fluoride. Acid fluoride means, remember in organic chemistry we say acid chloride, and that means RCOCl. So when I'm saying acid fluoride, it is basically RCOF. If we have this type of compound, then reaction is possible. Application. It is having application where high endurance is required. And examples are car brakes, car clutches, ceramic plates in bulletproof vest, and also in automobile industry, because in car brakes, car clutches it is required. Then high temperature, high voltage semiconductor electronic equipment. Manufacture of high temperature, high voltage devices as an abrasive and cutting material, because the compound is having some hard rigid nature. So that is why it can be used as cutting material. In the manufacture of electronic appliances such as LED and detectors. Now, problem related to carborundum. Which of the following are correct regarding carborundum? So here it is already mentioned, it is silicon carbide, but it may not be so. So that is why you should know what is actually carborundum is. So carborundum is silicon carbide. So which characteristic or more than one characteristic correct that we have to find? So it is saying the first one that each atom in this compound sp3 hybridized. The second one is saying that atoms are both sp2 and sp3. Now A and B, these two options together cannot be correct. Either one you have to choose. Right? Now remember the structure. There is only single bond and we have not seen any pi bond. So sp2 hybridization is not possible. So each atom is sp3 hybridized. That should be the correct, not the second one. Now come to C and D. C is saying that it is soft substance which melts on heating. But D is saying that it is hard substance which decomposes into elements. Elements means Si plus carbon. Now again C and D, these two together cannot be correct. Right? So either one of them will be correct. Now which one of this is correct? Obviously it is hard substance. It is not soft substance because there is large network structure. So among A and B, A is correct. Among C and D, D is correct. So these two are correct characteristic regarding carborundum. Next question. Now the next question, if you see, it is not just related to carborundum. There are some more compounds, but important point is it is related to carbon and silicon only. Now we have to choose the correct statements or statements. It might be more than one. The first compound, it is NMe3. It is saying that it is having pyramidal structure. Now NMe3, it is just like ammonia, only the difference is instead of hydrogen, ammonia is NH3, but now we have NMe3. So instead of hydrogen, now we have methyl. The fourth position of nitrogen, there is lone pair. We know nitrogen, there is total 5 valence electrons. So nitrogen is using 3 electrons for 3 carbon nitrogen bond and the rest of the 2 electrons, that is lone pair. And it is sp3 and that is why it is pyramidal. This is actually true statement. What about NSiH3 whole 3? Now these two are, there is some similarity. If you just replace carbon with silicon, you get the second molecule, NSiH3. Now in case of silicon, the difference between carbon and silicon is that carbon is from second period, silicon is from third period. Now in this case, there is no vacant d orbital, but here we have vacant 3d orbital. And because of presence of this vacant 3d orbital, this lone pair that is present over nitrogen, that can be donated to the vacant 3d of Si. This information I have already shared in some other class, where we have solved one problem that is related to this trimethyl amine and NSiH3 whole 3. So there it is detailed. You can also check that particular problem. So in case of NSiH3 whole 3, what happens? It is actually having planar structure. Why planar structure? Because the lone pair that is present over nitrogen, that is already donated to silicon. And there is double bond between nitrogen and silicon. Here there will be some negative charge and positive charge over N. Now after this type of back donation from nitrogen to silicon, there is extra pi bond. So obviously now it cannot be pyramidal, because if it is pyramidal, pi bond formation, parallel, that is sidewise overlap is not possible. So it has to be planar. So because of this back donation from nitrogen towards silicon, because of presence of vacant 3d, ultimately it is planar and it is sp2 hybridized. So this statement is actually, it is also correct. Then the third statement is related to carborundum. It is saying that it is highly volatile, but we have already seen in the last problem that it is hard substance. Only if you heat it at very high temperature, it will be decomposed to carbon and silicon. So it cannot be volatile. This is false. And the last one, SiO2 is called silane. SiO2 is actually called silica, or you can call it silicon dioxide, but it is not silane. But what is silane? Silane is actually SiH4. And see, you can find some similarity with the, if we pronounce methane, it is methyl, it is silane. That means similar type, it sounds similar. So methane is CH4 Just replace carbon with silicon. Now the term is silane. So SiO2 is not silane. This is not correct. This is false. So out of these 4 statements, the correct ones are actually A and B. Okay. Silicon tetrachloride. That is the next compound after silicon carbide. Silicon tetrachloride, it is simple structure, not large network structure like this. SiCl4. It is colorless, it is non-flammable, it is volatile liquid. Now it is liquid and there is pungent, suffocating odor. How we can prepare SiCl4? Here we can see some methods are there. So we can prepare it by passing dry chlorine gas over a mixture of silicon and carbon. So this is a mixture of silica and carbon, SiO2 and C, and we are passing chlorine gas over this mixture and there is formation of SiCl4 that we are trying to prepare, and carbon monoxide is the byproduct. But if we want to prepare it commercial scale, then that is large scale, then we are starting from silicon, that is the element silicon, and hydrogen chloride gas, not the liquid acid. In the gaseous form, hydrogen chloride, above 600 Kelvin, we are getting SiCl4 along with hydrogen gas. There are 2 more methods. There also we are using chlorine gas, but first we are treating it directly with Si, or we can also treat it with, chlorine can be treated with silicon carbide. So silicon carbide is also can be used as a source for the preparation of another silicon compound, which is SiCl4. So either you heat chlorine with silicon or silicon carbide, we get SiCl4. Okay. So these are the 4 methods by which we can prepare silicon tetrachloride. Properties. So some chemical reactions we will see here. How it reacts with water, which is hydrolysis. Now, just like SiF4 hydrolysis, where all the fluorine atoms replaced by OH group, here also all the Cl replaced by OH. So you get SiOH whole 4, which is silicic acid. Now, if you further continue the heating process, there is partial dehydration. So, if X, basically you can, if it is SiOH whole 4, you can also write it as 2H2O. So, SiO2 and 2H2O. So, if the water part is removed, it can be anhydrous SiO2. Then hydrolysis of SiCl4, if it is carried out at high temperature. So, what is the difference with the previous reaction? The previous reaction, we are doing the reaction in such a way that first there is silicic acid and then we are increasing the temperature. But suppose from that is initially if we start the process at high temperature, then you end up with finely powdered silica, which is already anhydrous and there is no water molecules associated with it. Fine. So depending on condition, in both cases we are getting SiO2, but depending on whether you are stepwise increasing the temperature or we directly doing the reaction at high temperature, depending on that, we can either get silicic acid or SiO2. Reaction with alcohol. Silicic, it forms silicic ester. So in the previous case, you have seen that SiCl bond that is replaced by SiOH bond. But when it is alcohol, instead of getting silicic acid where there is total 4 SiOH bonds, now we will get silicic ester because now we are treating SiCl4 with some alcohol. You can also write this equation in general way. Suppose the alcohol I am writing here ROH. Now this ROH, basically 4 ROH we have to take because we need total 4 OR group. So this OR group, now it will replace SiCl. So in this case, now we will get total OR whole 4. Okay, and along with HCl. Now in this case, if you take C2H5OH, which is ethanol, so if you take ethanol, basically you will end up with this molecule, because now your R group is ethyl group, or you can write C2H5. If it is methanol, it will be OMe whole 4. Fine. So it forms silicic ester. So we are calling this silicic ester. Basically, when we treat acid and alcohol, there is formation of ester. And you can find some similarity because here also this OR part, it is now attached to Si. So that is why we are calling it as ester. So SiCl4 is substituted by the nucleophile OR group. For C2H5OH, it is C2H5O minus. And this is nothing but alkoxy ion. That is the RO part of alcohol. This part is basically alkoxy ion. That is RO minus. So if it is ethyl alcohol, we are getting tetraethoxysilane. See, now we are using the term silane as if 4H atoms replaced by OR group. So it is as if silane derivative. SiH4 to SiOET whole 4, tetraethoxysilane. Reaction with hydrogen. Now here basically reduction is happening. Reduction of SiCl4, and this is the reducing agent. We are getting silicon after reduction, and Cl is now with H. Now it is HCl. So these are the reactions of, that is the chemical properties of silicon tetrachloride. Application. As a starting material in the large-scale synthesis of silica gel. So SiCl4 we can use to make silica gel, because see, in the previous slide we have already seen these two reactions where basically silica is the final product. That means you can use SiCl4 to make silica. Then you can use it to make silicic ester also. It is a binder for ceramic materials. Then in the production of photovoltaic cell, to prepare high purity silicon, that is you can use SiCl4 to make Si itself, that is the element silicon. That also we have seen. Look at the last reaction. Reduction of SiCl4 with H2 gas, we are getting Si. That means you can produce Si also. So high purity silicon we can get, and silicon itself is very important for making transistor, computer chip, solar cell. So these are the applications of SiCl4. Here we have a question related to SiCl4. Which product is formed when silicon tetrachloride reacts with water? Remember, it is very easy to remember. It is simply replacement of all the Cl with OH. But if you do so, what you get? You get SiOH whole 4 first. But remember, if we further heat it, there is loss of water, and ultimately we get SiO2 along with HCl. So silicic acid, it is not present in any of the options. So obviously you have to choose that option where SiO2 is present, and there is no such compound like this. So you can easily eliminate these two options. So we are only left with SiO2 HCl. And see, this is actually this reaction. SiCl4, final product SiO2 HCl. So here correct option is this one. Assertion reason type of question. Assertion is saying a molecule of silicon tetrachloride is nonpolar in nature. Now whether it is true or false. Remember, SiCl4, though we have not said anything about structure, but actually see, it is very easy to understand. As silicon, it is having total 4 valence electron, and there is total 4 SiCl. So obviously its arrangement will be tetrahedral, and whenever it is tetrahedral, all the bond angles are same, right? And it is sp3 hybridized. Now because of the same bond angle, even if you consider polarity for this bond, because chlorine is more electronegative, so direction of polarity for individual bonds, it will be like this. But because of this tetrahedral arrangement, all the dipole moments, ultimately it will cancel each other. And as a result, the final polarity of the overall molecule, it will be actually, there will be no polarity. And that is the reason why it is non-polar. So non-polar, this molecule is non-polar. This is actually true. But why it is non-polar? because here all the angles are same because of this particular tetrahedral environment. So all the 4 bonds in SiCl4 are identical and the molecule has tetrahedral structure and the angle is 109 degree. So this should be the correct option because individually both the statements are correct and the reason statement is actual explanation for the assertion statement. So that is why option A is the correct option. After finishing silicon tetrachloride, next compound is silicone. Now look at the spelling. It is not silicon. Silicon is S-I-L-I-C-O-N, but it is silicone and not just silicone. Here it is written as plural form. That means there may be different types of silicon. So that is why we are saying it as silicones. So what is silicone? Silicones are actually a type of polymer. What kind of polymer? So it is that kind of polymer where the monomer unit is siloxane. Next question arises, what is siloxane? Siloxane is actually having this type of unit, oxygen silicon backbone. And not just oxygen silicon backbone, here the Si atom is also attached to 2 organic group. Suppose R group, and these are maybe methyl, ethyl, some other alkyl group, propyl, or even phenyl group. So when we have this type of monomer, SiO-Si linkage is there. Si is also attached to 2R group, that is organic group. Then this is the monomer unit, and this type of monomer unit when connected to each other, now we get the polymer, and that we are calling as silicones. So remember that the monomer unit is siloxane. So these are the different structures because there are different types of silicone. The first structure, as you can see, it is linear in nature. And the repeating unit that is mentioned within third bracket with n, that means n times it is repeated. And if you look at the left hand side, this side is actually blocked because instead of 2R group, now this silicon is attached to 3R group. Because if there is further, that is any other atom, then this side has to be continued. But this side is not continued. It is blocked this left hand side. The continuation is happening this side. So when there is 3R groups, one side will be blocked. Then for the next one, it is cyclic. So there is no such continuation. And look at the structure. You have SiO-Si linkage, and each Si, it is connected to 2R groups. The third one is cross-linked silicone. So in cross-linked silicone, if you are looking at this part, it is just like linear silicone. That is the first structure. Suppose this is number 1, this is number 2, this is number 3. See, if you focus on this part, it is just like the first structure. But see, this silicone, it is attached not just to oxygen, but it is also attached to 2 more oxygen. That means this side, the chain can be continued. Also, downward, the chain can be continued. Only when silicon is having 2R group, 2 oxygen, then this is continuing as linear. But suppose both sides there is total 4 oxygen, so this side can be continued because there will be another silicon and R group, then another silicon, sorry, another oxygen. So that is why it is called as crossed linked, not just linearly it is continuing, it is cross linked. Here the repeating unit is R2SiO. R2SiO is the repeating unit. And the general empirical formula, that is why we can mention it like this, because depending on this repeating unit. They were named silicone. There is a reason for it. Empirical formula is R2SiO. Now we know ketone, the general way we represent ketone is like this, which is nothing but R2CO. Similarly, if you look at the empirical formula, it is also R2SiO. Only in place of carbon, now we have Si. Because of this similarity in the, though it is not the full formula, it is just the empirical formula because it is the repeating unit. But still it is having some similarity with the ketone structure. So that is why, just as we have the spelling ketone, it is also we write it as silicones because of this similarity. Because of its very high thermal stability, because thermal stability obviously it will be there because it is polymeric, and not just normal polymers, it is also having some resistance towards heat. So it is high temperature polymer. This is the specific characteristic for these compounds. Okay, not just polymer, high temperature polymer. How we can prepare it? First of all, before going to the actual preparation process, we have to know how we can prepare this molecule, which is dialkyl dichlorosilane. It is also silane derivative. Remember, silane is SiH4. Now, suppose you are replacing 2 hydrogen with 2 chlorine and 2 hydrogen with 2 argon. So that is why we are calling it dialkyl dichlorosilane. Now, R2SiCl2, or if you have this R group with benzene ring or benzene derivative, it will be diaryl dichlorosilane. Now, these two types of molecules, first you have to make. How you will make it? Look at this equation. You have to start from silicon and RCl. So suppose you are making Me2SiCl2, you have to start from methyl chloride, MECl, okay? Or if it is PH2SiCl2, you have to start from chlorobenzene, PHCl, okay? So in this way, it is prepared by passing vapors of RCl or ArCl over silicon element at 570 Kelvin with copper as catalyst. So first we have to prepare R2SiCl2 or diaryl dichlorosilane, and then we will use this molecule as the starting material to prepare ultimately silicon. So here we have this R2SiCl2. This molecule, if we write it like this, R2SiCl2, now we are doing hydrolysis reaction. What will happen? These 2 chlorine now replaced by 2OH group as if HCl is removed. Now this molecule, if you take 2 times, suppose you have taken 2 molecules, and here if you remove one water molecule, you get SiO-Si linkage, right? Now the third, suppose this is number 1, this is number 2. Now you have also taken a third molecule. Again one water molecule removed, another SiO-Si linkage. So in this way you can continue the process, right? But suppose you want to block the chain somewhere. What you will do? Now you have to treat it with R3SiCl. So if you want to block it, if you take it, that is if you treat it with R3SiCl, now what will happen? This Cl and H will be removed, and in this side you will get 3R group, and there is O, then Si, and it will continue. So in this way you can block, but for blocking you have to use R3SiCl. So hydrolysis of dichlorosilane, that is R2SiCl2, it's a straight chain polymer which can grow from both sides. But if you want to control the reaction, that is if you want to block the reaction, then you have to use this specific, where you have total 3R groups. So when there is 3R groups, further chain continuation process is not possible. Fine. Now, if we do the same process with, suppose instead of taking R2SiCl2, if you start with this molecule, RSiCl3, then there is a chance of formation of complex cross-linked polymer. Why? Because now instead of 2R, you have only 1R. That means another total 3 chlorine. So there will be total 3 OH, right? When you are doing hydrolysis. Sorry, it is Si. So instead of 2 OH, now you have 3 OH. So you can continue the chain 3 sides. So that is why there is a chance of complex cross-linked polymer. But in that case, you have to start from RSiCl3. Then linear silicones can be converted into cyclic silicones when water molecules are removed from the terminal OH. So suppose you have taken total 3 R2 SiOH whole 2. Just remember in the previous slide. Here we have total 3 linkage, right? So you have to take total 3 R2 SiOH whole 2. So if you take it and remove water in this, that is keeping the arrangement as if it will form cyclic, you can also make the cyclic structure. Okay. So these are the preparation methods of silicones. Next we will also see its properties and application and also some problems. So we will end the session here because if we start the properties part, we will not be able to finish. Okay. So we'll start in the next class. So we are ending in the preparation of silicones in this slide. Thank you for listening.